And let's start now. Okay, so in order to solve this problem, let's see, the normal stress in this guy, because it's experiencing an axial load, let's call the axial load that is applied to this guy F. Questions? If the axial load is F and the cross-section area is A, the stress in this guy will be force divided by area. And if you don't want the rod to be subjected to normal stresses greater than 800 megapascal, so this has to be less than or equal to 800 kilopascal. Instead of F, we have the value that is, or actually I can further simplify this equation. Instead of A, I can write pi r out squared minus pi r in squared. And this has to be less than, let's call this sigma 0. This has to be less than this sigma 0. So then from here, I can easily say, therefore, F divided by pi sigma 0 has to be less than or equal to r out squared minus r in squared. So this is, I just brought this here and I brought this here. And so then I can rearrange that and I can say r in squared has to be, I bring r into this side and I take this guy to the other side. Right? And so what follows from here, I'll continue here, is that Ri has to be, so IR maximum will be equal to square root of R out squared minus F divided by pi sigma. Does this make sense? Any questions on this so far? And so now, how do I proceed to, I have so many units here, like kilonewton, kilopascal, and then R0 is in millimeters, R out, I'm sorry, is in millimeters, that I may prefer to present everything in basically SI, standard SI units. 50 millimeters is 0.05 squared, minus F is 4,000 newtons divided by pi, and that is 800 kilopascal, 1,000. And when you do all that, you get the value for R0, I'm sorry, R in, which is going to be 0.031, and it's going to be in meters because we're dealing with standard SI units, or 31 millimeters. And this is the maximum value of Ri or Rin, because it's because we have this inequality. Ri squared has always needs to be less than or equal to this. So the highest value it can have is this itself, which is what we used here. Any questions on this? Okay. So let's go to another problem. This problem. I give you 5 minutes to solve the problem. And I am interested to know who gives me the final right answer. So 5 minutes from now. How close are you guys? Anybody?
I think I have an answer.
What is the answer?
4.5 pounds per inch squared.
Excellent. Good. Right. That's the right answer. So let's do it. Okay. So tell me, what is the first step?
Draw a free body diagram.
Excellent. Thank you. I appreciate that. That's exactly right. So, so free body diagram of CBF. What forces do you put there? I mean, this force, I put it for you. What else? This is force F. This is not point F. This is force F. What else do you put on this guy?
The forces and the pin supports at C and B.
What would you put at C?
The force in the Y direction and the force in the X direction.
Good. What would you put at B?
Force in the Y and force in the X.
Is there a force in the X at B?
No. Well, no.
Why not?
Because it states it's perpendicular.
And AB is basically a two-force member, right? So it can only apply vertical force. So basically, if I draw the free body, that B has only this point and this point. It's a two-force member. So the force in AB is axial, and that force is transferred to, exerted from AB by AB to CBF. So that's the force. And it can be up or down. It really doesn't matter. So actually, and so the free body diagram of AB, if I draw it like that, would be, in what direction would I put the force here? Up or down?
Down,
Why?
because you want it to cancel out with the B in the other free body diagram.
So you're right, it's in the opposite direction, but I wouldn't call it cancel out, because this force is applied to AB, this force is applied to CBF. So they're applied to two different bodies. They don't cancel out, but they're action and reaction, these two. So that's the more appropriate reason. So now if I draw, I have this, and the question is, what is the normal stress in AB? If you think about this, if I write equilibrium of AB, all I know is that this is equal to that, but I don't know the magnitude of this force. So I'm going to look at equilibrium of CBF. And equilibrium of CBF, what do I get for equilibrium of CBF? What are the three equilibrium equations for CBF?
Sum of forces in X, Y, and then moment.
Exactly. Sum of the forces in the X is 0. And what does that tell me?
It says that it's static, it's not accelerating.
Oh, wait, I see why it was deleted for some reason. Yes, that's right. But what do I get out of it from this equation?
There's no force at the pin support at C in the X direction.
Good. Cx has to be 0 because there's nothing else in the X. Sum of the forces in the Y direction 0. What does that give me?
An equation with two unknowns.
What is that?
Well, it's going to be the positive force F,
Okay.
positive force B, and the positive force CY. And that's all going to be equal to 0.
Which means that I'm wrong at least in one of them. One of them has to be negative. I mean, which is these two.
Most likely it's going to be B.
Good, excellent. And so let's look at equilibrium. I take equilibrium with respect to this point, moment equilibrium. So with respect to C is equal to 0. What does that tell me?
It's going to give you the force of B.
Good, excellent. So I will have F times 6, because that's from here to here is 6, from here to here, plus B times 4, from here to here is 0. And if I put, instead of F, I put the 6 kips. This is foot and that is foot. So from here, I get the value of B, which is going to be, B is minus 9 kilonewton. I'm sorry, minus 9 kips, not kilonewton. So now, what does minus mean? Means it's not in this direction. It is going down. And means this, I have to change the direction of that here and that there. So basically, if I want to redraw B, it's like AB, it's like this. with a little bit of artistic talent, it's like this. And so this is 9 kips applied here. The question is, what is the normal stress in this guy? And we say the normal stress is equal to what?
Force divided by area.
Which, exactly, force divided by area. So the force is B and divided by area. What is the force here? The magnitude is 9 kips.
Mhm.
What
And
is
the
the
area is going
area?
to be the. This will be 2 inches squared. Since it's in kip, we can just leave it in inches.
Exactly. And it's going to be, as you guys said, it's going to be 4.5, and it's going to be KSI, kilopounds. K is for kilopounds square, a per square inch. Okay. Okay. Any questions on this one? Okay, so let's go to the next one. It's a little bit more complicated. Well, just a little bit, tiny bit. So we have a truss like this. The force F is applied here. The cross-section area of each of the bars is given. What is the normal stress in a plane that is perpendicular to the axis of each rod? So I give you a few minutes to tackle it. Thank you.
Professor, what was the area again one more time?
you see it now?
Yes, sir.
I think I have an answer.
What is the answer?
5.75 KSI.
Close.
I got a little bit different. I got a different answer.
What is it?
I got 2.872.
No.
4.89.
Yes,
4.9.
exactly. That's right. So, okay, let's give it just one more minute and then we can solve it. Okay, so let's let me see if I, okay, yeah. Okay, so let's solve it. What is the first thing you do in solving this problem? Anybody?
Free body diagram with the at the pin where the F force is applied.
Good, excellent. So basically, if this is point F, I put this force here, and I have two forces. Let's call it 1 and 2. So I have this P1, and I have P2. Okay, and so this angle is beta, which is the same as this angle beta. And so let me also draw the axes, the X and Y axis. So this is my Y axis and this is my X axis. Okay, so I drew the free body diagram. What next?
Net force equations.
Where? Which one?
Y direction.
Okay, sum of the forces in the Y direction equal to 0. And what does that tell me?
P2 cosine 40 plus P1 cosine 40 minus F is equal to 0.
Cosine or sine?
Sine.
Exactly. P1 sine beta plus P2 sine beta is equal to F. What does sum of the forces in the X direction equal to 0 give me?
Nothing.
It sure gives me something.
P1 equals P2.
Exactly. So basically what it gives me is that P1 cosine beta minus P2 cosine beta is 0, which means, so then naturally P1 becomes equal to P2. This is what you can also call symmetry condition, okay? So if you just don't write that and then just say because of symmetry, P1 and P2 are equal to each other, that's also true. So then when I put this P1 equal to P2 here, what I get is that P1 is equal to P2 is equal to F divided by 2 of sine beta. And so if you put the value of F is 3 kips, you put it there and beta is 50 degrees, you get the value of force that is this much. And then the next question is, what is the normal stress? You just say force is the normal normal stress is the axial force divided by the cross-section area. And this is 1,960 pounds divided by this 0.4 inches. So the answer would be 4.9 KSI, as some of you said. And you were correct. Okay. The next problem is, any questions on this? So the next problem is this, 3.28, cross-section of bar BC. The cross-section is shown here of BC and DG. This is a cross-section. Imagine that the bars are made of a material that safely supports a shear stress of up to 240 megapascals. So the key here is this shear stress that they can undergo. Yeah. What is the maximum safe value of the force that we can apply here? So see if you can solve this. I give you 5 minutes to try to solve it. Did anybody solve it?
$216.
What is the unit?
Based on what's maximum safe height. Kilonewtons.
Close, but how do you solve it? How did you solve it?
I used the shear stress given, multiplied it by the cross-sectional area to get the force in the members, and then I took the moment at D of the bottom member with the force acting, and then plugging in the force that I found earlier for B, since it could be, I assumed that it could be considered a 2-force member, and then I solved it that way.
Probably you're correct. I mean, I think you're correct. The approach I would choose is a slightly different, but that's probably is because I've solved many more problems than you on this topic. So the first thing I do is, as you said, CB and GD are 2 force members. So if I draw the free body diagram of this guy, I see the force F, I see the force dg, so let's call it F dg, and I see the force F bc. Okay? Now, if I write equilibrium for these three, for this body, for this guy, so keep in mind, FBC is the force that is applied to this bar by this guy. FDG is the force applied by this guy on this guy. Okay? So if I write equilibrium for this guy, for them, I can say sum of the forces in the x equal to 0, and this literally doesn't give me anything because there's no force in the x direction. If I say sum of the y forces with respect to y is 0, then I get FBC plus FDG is equal to F. And if I say sum of the moments with respect to, let's say, point B is equal to 0, what I get is that, and here I'm going with clockwise positive, so I'm getting F times 1 meter. And by the way, I put each length in meters. So F times 1 meter minus F dg times 0.6 meters, which is from here to here, or from here to here, equal to 0. And if I do that, I solve these last two equations, I get FDG is nothing but 1.67 times F, and FBC is minus 0.67 times F. So whatever the unit of F, I just I put F there with whatever unit, and I get FBC or FDG with that unit. But here F is unknown. But I can make some advances here. So the next thing is I say I can calculate, let's start with DG. In DG, remember, this is the force that is in the axial force in DG. I can say the sigma normal stress in DG is going to be what? How much is it going to be?
It's going to be 0, right? Oh, no, in DG.
DG. Some force divided by some area. What force and what area?
Force DG.
Force DG.
Good. And so basically, it's going to be 1.67 F. And divided, I assume that everything is standard SI units. So divided by the area, and the area that I have to put there is this area, which is 0.06 times 0.01. So it's going to be 0.06 times 0.01. And if you calculate that, the answer you get is 207.80 F. Now, here you have to be really careful about units. Because here I have force on the left side, I have a stress. So you need to have a record of the units that you used. Here I used everything in SI units, meters squared. So from this point on, I just put a note here that I have to use F in newtons, and this stress is going to be in Pascal. I don't know what F is, but all I'm saying is if I put F in newtons here, I will get out stress in pascals because it's Newton per meter squared. Does everyone agree with me?
Yes, sir. Why are we solving for the normal stress?
Good. Because, good question. So now let's take a step further. In axially loaded bars, that there was a force applied, axial force. You remember that the maximum normal stress was what? If the cross-section area was A. What was the maximum normal stress? Any suggestions?
240 megapascals.
It was just F over area, right? The maximum normal stress in just this problem. And what was the maximum shear stress?
$240 megapascal.
No. I'm opening a tangent here. I'm just asking you to think about this problem that I am showing you on the slide. There's an axially loaded bar that has a cross-section area A, and there's an axial force F. In this guy, what is the maximum normal stress? F over A. Do you guys agree with this?
Yes.
What is the maximum shear stress? So let me ask you a question this way. On this plane that is normal to the axis, do I have any shear stress? Or I only have normal stress?
Should only have normal stress if it's axially loaded.
Exactly. Now, if I look at it at an inclined angle plane like this, will I have only normal stress or will I have shear stress as well?
You'll have shear stress as well.
Good, excellent. And so on this plane, I will have normal stress and shear stress. And as a matter of fact, if the tau, let me just find my eraser. The tau on any plane that makes an angle theta with the normal plane will be force divided by area times sine theta cosine theta. Do you remember this equation?
I still don't understand how we derived that equation.
Which one? This one?
Yes, sir. The tau equals F over A sine theta cosine theta.
So in your class, when you look at an inclined angle, you see, so let me solve this problem for you. So if you look at, if I draw the free body diagram of this portion, on this guy, I see the force F, I see the normal stress sigma, and I see the shear stress tau, right? Do you agree with me so far?
Yes, sir.
Okay. Now, if this angle is theta, and this area is A, what is this area? This angle is theta. So if you look at this triangle, this area is A. What is this area? Any idea?
It's A divided by cosine theta.
Good, excellent. Because this is this times cosine of the theta. So this area that I call it A of theta is A over cosine theta. Now, if I write equilibrium for these two, what I get is force F has to be equal to this sigma that I call sigma theta because it's at a plane that makes an angle theta, times A of theta, which is here, defined here, times cosine of theta because this angle is also theta. And then tau is helping with the force, so that's going to be minus tau theta, A theta, sine theta.
What angle is also theta? Is it the angle between the horizontal and
This force, the normal stress,
okay.
right? Because this is perpendicular to that, this is perpendicular to this. And this is for equilibrium in the x direction. In the y direction, I need to have sigma theta, A theta, sine theta. That is the vertical component of a stress, force caused by stress, plus tau theta, A theta, cosine theta have to be equal to 0. When you solve these two equations for sigma theta and tau theta with a known A theta, you get this equation. Okay, and you'll do it in the class. So basically that means if I take this plane versus this plane versus this plane, the magnitude of shear stress is going to be different. On which plane, which of these planes, 1, 2, 3, or any of them in between, will tau be maximum?
Whenever the plane is exactly parallel with the force.
On that plane, theta, you mean theta 90 degrees, you mean?
Yes, sir.
Then it's going to be 0. Because this term is going to be 0.
It'll be 45 degrees, right?
Exactly. At 0 and 90, this is going to be 0. You can easily calculate the derivative of that, set that equal to 0, and then you will see it's 45 degrees. But if I put 45 degrees there, I get basically this. Tau max is F over 2A, which is half of the sigma max, which is and sigma max happens on this plane, tau max happens on this plane. Did you guys follow so far what I said?
So I guess just for some clarity here, like
Yes.
the vertical plane, you know, and I guess inherently I would think that would be the least or the most shear stress because it's like straight through the bar, but so it's maximized at 45 degrees.
Exactly, because on that plane, the area is also going to be very large. And the stress, even shear stress, is force over area. See, when I make this plane, so let me redraw it here. When I make the plane go like this, I am constantly increasing this area.
Okay, I got the nomenclature backwards. We're saying that the highest shear stress that it can handle is at 45 degrees.
The highest shear stress happens at 45 degrees.
Okay, okay.
So now let me open a new slide. So a recap of what I said is basically the following. If I have a bar that is experiencing axially loaded force, maximum normal happens on this plane. Sigma is going to be max and tau is going to be 0 on this plane. And at a 45-degree angle, so 45 degree, so on this plane here, tau will be the maximum value that the bar will experience. And this tau max is going to be half of this sigma max. So sigma max and tau max do not happen on the same plane. They happen on two different planes, the normal plane and the 45-degree angle plane. Okay? You guys follow me so far?
Yes, sir. Could you go back one slide real quick? I just wanted to write down the equivalency you wrote. Thank you.
Okay, so now that we have this brilliant equation, we can solve the problem because the problem told us, now I go to the problem, it says the maximum shear has to be this much. And now we know the maximum shear is half of this. So basically, I can say the tau max in dg is going to be half of this. This is the maximum normal stress, and the maximum shear stress is half of that, which is this. Again, don't forget the units. I put newtons here, I get megapascal here. So this value has a unit. The unit of it is 1/meter squared. Now,
So
yes.
just a real quick question. So the bar is acting vertically at BC and DG, acting basically like straight up and down there. Are we just saying that the torque max would be like if they would move to the 45-degree position, or
No. What we're saying is that on a plane that is 45 degrees here and here, the shear stress will be the maximum, and that maximum shear stress has to be less than 240 megapascal.
So basically with them loaded axially right now, there's basically a shear stress occurring at a 45-degree plane of that
Absolutely,
much.
yes,
Okay, thank you.
Exactly. So this shear stress has to be less than 240 megapascal, so times to the power of 6 Pascal, because I want to compare Pascal with Pascal. Now, this is about dg. I can do the exact same calculation for BC. Basically, I take the magnitude of the force divided by the area. That gives me a new value for normal stress divided by 2 to get the maximum shear stress. So let's do that. So basically, sigma of BC is going to be the force, which was minus 0.67 F divided by 0.01 times 0.06. And this answer is going to be minus 1110 F. Therefore, tau max in BC is going to be half of that. I'm just interested in the value of that. So I calculate the absolute value. It's going to be 556 F. This also has to be less than 240 times 10 to the power of 6 Pascal. So I have two inequalities for F. One is this guy, and the other one is this guy. And obviously, this one gives me a more conservative value for F. So basically, or in other words, the F you get here from this inequality will be higher than the F you get from this equality. So basically, the F you get from this one does not satisfy this one. That's why you have to use this one as your measure. So basically, the final answer is that I will rewrite the equation from the previous one, 1390. So 1390 F has to be less than or equal to 240 times 10 to the power of 6 Pascal. Therefore, F has to be less than or equal to 173,000 newtons. So the maximum F we can get is, okay, it means if you put any larger F, what's going to happen is that the shear stress that will exceed the maximum value. So the key to this problem is understanding this figure right here. Okay, these are the problems I had for you today. Any questions or comments? You got your homework 3. The solutions will be become available tomorrow night. And the next quiz is next week, Thursday in the class. Any questions or comments? Okay, thank you guys, and see you on Friday. Bye.
Thank you.